I mean, most people just if they bring up the single thing about fluid mechanics, this is the equation, right? So this is again just a quick, the overview of what we want to discuss this week. This is all right. I mean, you don't need to worry about too much, but basic idea is we'd like to start from we start from the control volume analysis, but the discussion is going to be idea is essentially Navier Stokes equation is we would like to perform the control volume analysis at every single location in the space, right? If you are doing this, how much flow coming in, how much flow coming out, as well as the F equal MA at every single location in the space, that is going to give you information of the entire flow field. Okay, so this is what we want to do. Then we'd like to derive the subset of equation that's called Navier Stokes equation, and then that is hopefully we finish the derivation today. And then tomorrow we are going over a few different examples. One is weight flow. This is actually this week is quite interesting. It has a lot of summary from the previous week, right? So we talked about weight flow earlier in the week, earlier in the semester. Okay, this is there is when you have a low viscous fluid, you pour it, right? You create a linear velocity gradient. And then that time I said, okay, please trust me. And then just it's going to be linear, right? Without any derivation. But in fact, we are finally doing the some derivation. Okay, in fact, when you have that condition, the flow profile must be linear. We are finally deriving it. Hopefully tomorrow. We also have a parabolic flow profile, which we call this a Poisson flow. So Poisson flow is we also said, okay, I give you this quadratic equation, right? Then okay, let's start from there. Right? We never without any deriving it. But the good thing about this is by using Navier Stokes equation, we can also derive that mathematically. And then we can combine both of the flavor of the fluid flow and then Poisson flow. Okay? That's about it. And then so that's something we want to start this week. Okay, so to start this week's discussion, right? Just recall here, control volume analysis. Okay, so far, we have been looking at something big. Okay, let's call this is the global, as opposed to the local we talk about later. So something like previously, right? Our discussion of the control volume analysis is we have some material volume, and then we consider control volume, which is just coincide with the global things, and then there are some flow coming in, flow coming out. Then see, okay, how the materials flows going to be different. But today's discussion, we still apply sort of similar idea, but okay, let's see what we want to do today. We want to consider something called local analysis, which is instead of looking at the super big control volume as this, let's look at the relatively small control volume, or in fact, this is not a relatively small, infinitesimal control volume. Then, okay, let's say this particular location, we know this is x, y, z. This is the location. Then we know this length. This is okay, delta x, delta y, and then this length is the delta z. Okay, so we have this cube, and then we want to perform the control volume analysis for this cube. Okay, that's something we want to switch the view, right? So as I said, the fundamental idea is if you perform this control volume analysis at every single location in the space, that is going to give you the equation for the entire space. That's the idea. Okay. By the way, when you do this, it's sort of a black box. But when you perform this CFD, right? CFD, when you do this, for those who must start touching it, you see some mesh, right? That this triangular mesh, and that is in fact nothing but the control volume. Right? So as you actually making those those meshes smaller and smaller and smaller, you are going to have more smooth, the more information regarding the flow. Right? So this is a theoretical, right? But again, this is a theoretical. I mean, in fact, if you don't have a time, you cannot check every single location. But by concept, as a concept, right? If you perform this control volume analysis at every single location in the space, you get the equation. So that is something we want to start from. Okay. So perform control volume analysis at every single location in the field. Then no information of entire field. Okay. This is more or less like the concept that we are trying to employ today. Okay. Any questions to start with? Okay. So then let's start with the control volume analysis. By the way, this is basically what they are saying here. Okay, we are considering this super small infinitesimal cube, and then see what is coming in and what is coming out. Okay. So this has a name. Okay, we have this local analysis. This local analysis by this name. This local means the specific point instead of looking at the big point. Okay, so that's something we start. Okay, so let's do the first continuity equation. This is about mass conservation, if you remember, right? So you do have this, okay. This volume, right? Infinitesimal volume, and then there is some the flow coming in, flow coming out. Potentially, this thing can happen from the whole six surface, right? Okay. So let's just this is the point we come back later. But we do have this. If you remember, Reynolds transport theorem is giving you dm dt of the material volume equals to dm dt of the control volume plus integration of the control surface rho times v dot dA. Okay. This is the this is the control volume analysis, and then if you remember the argument, this left hand side should be equals to 0, right? Because of the mass conservation. Because of the mass conservation. And at this point, we haven't made any assumption regarding the steadiness. Okay, so we don't know, whether this particular thing is steady or not. But let me just say this is the control volume plus. Okay, if you remember, right, how we describe this, basically this is the m dot of the net, right? Net means the outflow minus inflow. Okay. Remember a little bit, right? I mean, we discussed this, right? Outflow we always say positive, and then inflow we say negative. Okay, so we do have this equation. Overall, okay. Overall, we have this equation. 0 equals to dm dt of the control volume plus m dot of the net. Okay. So now we want to analyze what are each term corresponding to this particular case. Okay. So in this case, okay, let's say the first, let's call this is the A, let's call this the B, and then first let's first analyze A. Okay. So to explicitly describe A, which is the dm dt of the control volume. So in this case, this is actually not bad. This this is not bad. In fact, just remember, right? The goal, this M mass is always described as the density times volume, right? So it's density times volume. Okay, and then in this case, we are particularly interested in the materials that happen to be inside of this control volume, right? And then this control volume, okay, I didn't clearly specify, but let's say they consider stationary, non-deforming, infinitesimal control volume located at x, y, z in this particular space. Okay, so this is this is not this is let's say stationary, and then also the non-deforming. So let's say given this information that this control volume is not deforming. Okay, if this control volume is not deforming, right, we can say this volume V can be described using this dx, dy, and dz, right? Okay, so this is nothing but rho times delta x. So this delta x times delta y delta z. So this is going to give you, this is quite not bad. It's going to be a ddt of d rho times delta x, delta y, delta z. Okay. So and then in this case, right, this actually requires a bit of thinking here. Now let's consider this delta x, delta y, delta z is going to be, this is a fixed number, right? And then now we are concerned for the specific location. Eventually, so this is something okay, you sort of have to think about a little bit. But in this case, we are going to look at x, y, z at any location. But at this point, we are going to look at the specific x, y, z. So in a sense, we are treating x, y, z as a location, as a constant. Okay? So now ddt is going to be in theory this entire thing has a 4 variable, right? X, y, z, and t is going to be the variable. But now we are treating those x, y, z as a constant. So you take the just this the derivative here. This delta x, delta y, delta z is constant, and then we are concerned with the particular location with the fixed x, y, z. Therefore, we are looking at the partial derivative d rho dt times delta x, delta y, delta z, which is outside of this derivative. Okay, so that's essentially it, right? Okay, so alternatively, we can also write this as d rho dt of d b. This is also fine. Okay. Any questions for this? This is sort of the end point.
That means you fix each of the x at a time, is it? That means you fix x, then your y and z are free, or all are fixed at the same time?
Oh, we are looking at they're all the same time. Yeah,
okay.
We are looking at the particular location. We are concerned with a particular location in the space when you have thinking about it, right?
Then if they're all fixed, why do you have to use a partial derivative rather than
because in theory this is we are looking at this, but what is the 4 variables for rho? For any fluid parameter, right? What are the 4 variables? X, y, z, and t. Right? And then now we are considering x, y, z as the sort of fixed location. So therefore, the only remaining variable is the t, right? And then that's the meaning of the partial derivative. When you take a partial derivative, except for that one variable, you are considering the rest of the variables as a constant. Okay? That is the yes. Sorry, yeah.
Essentially, the fluid is no longer incompressible.
Okay, so in this case, we haven't made any assumption, right? So yes, that's a good question. At this point, fluid may be compressible, right? But we just haven't made any any assumption here. Yeah. Any other comment here?
Your camera damn sharp.
Sorry.
Your camera damn sharp.
Okay, then I have the expression for the A. Okay, now let's find the expression for the B. Okay.
Video.
Let's look for the expression for B. In this case, now we want to know the M of the net. This is the mass flow rate of the net. I think it's
M over dt for control volume. That is the inflow, right?
M, which part?
Or part A.
Part A. dm dt of the.
Yeah, what is that the inflow?
This has nothing to do in flow or outflow. This is the whatever is inside of this control point.
Then on top we write the outflow minus inflow.
This one is for the M dot net.
Oh.
Right. So if you remember this control volume analysis, right? You have two terms on the right hand side. The first term is how this, locally, how this variable is going to vary. And the second term is the flow in and flow out. Right? Yeah, thank you very much. So this is I think this is a good review of what we did in the before the midterm. Okay. So the B is the M net. Okay. The mass flow, net mass flow, right? Now, okay, to consider, to analyze this, right? We are looking at the infinitesimal volume. So now let's consider the three different directions where materials comes in and out. So this is supposed to be M net in the x direction, M dot net in the x direction, M dot net in the y direction, M dot net in the z direction. And then in this case, let's just consider first, let's just consider the one part. Okay. So consider M dot net in the x direction. And then to consider this, okay, we like to, what we want to do here is let's see the side view of this box. Okay, this is the cross-sectional view of this box. And then as we sort of say, right, okay, let's say this is the x coordinate. We said the location of this box is x, right? Okay, and then we also set the length of this box. This is a delta x. So if we just look at the coordinate on the front side, let's say this is the x plus delta x over 2. On the back side, it's going to be x minus delta x over 2. Okay, is okay. And this is more like just setting up the coordinate here. And then there are some the flow. Okay, there are some flow that's in the x direction, which is coming in and coming out. Okay, and then at this point, the velocity here is going to be u. Is u evaluated at x plus delta x over 2, right? And then on the back side, this is the velocity u, which is evaluated at x minus delta x over 2. Okay, so is this okay with this setup? Right? So now what we want to know here, right, is the M net in the x direction. Now from here, right, now you can consider, you can potentially, by the way, if you want to know the, we are looking at this segment from the side, right? But this is the sum the surface, right? And in this case, this is the area. What is the area? What is the size of the area? How can you describe this area?
It's a square, it's a cube, right?
It's a cube, yeah.
So it's just delta x squared.
Yeah, it's a delta. Yeah, okay. So this is a cube, but I define this as the two other variable, right? Which is on the side. So delta y and the delta z is the two coordinate, right? Which, if you look at this cube, this is this rectangular box from the side. The side length is the delta y and delta z. Okay, so this delta a is delta y, delta z is the area, right? For the both sides, right? So this is actually not bad. Now let's consider what is how can we describe this m net for the x. which is the rho times u times delta A.
What's the U again?
This is the mass flow rate, right? Which is evaluated at x plus delta x over 2. This is the inflow. And at this point, right? I mean, I just use these values in this. We just use if the flow direction is opposite, it's going to be just opposite, right? The sign is going to be opposite. So it's going to be rho times u times delta A, which is evaluated at x minus delta x over 2. Okay. And then in this case, one thing you can see here is the delta A is constant. Okay, delta A is constant. You can take it out. So rho times u, which is evaluated at x plus delta x over 2 minus rho times u, which is evaluated at the back surface times delta A, and then where delta A is the delta y delta z. Okay, so let's just say delta y delta z. Is okay. Now I do one of the quite common trick. You may have seen in this class, or I think you have seen this class a few times already. What you want to do is the sort of sacrificial variable. You multiply everything by delta x, and then divide everything by delta x. This is some common trick that we often use. Okay, so when you use for this part, right, first part, considering delta x is super small, infinitesimal. When you have this delta x very small, what is this first bracket value look like? It's a derivative, right? I mean, it's a derivative of this quantity rho u with respect to x. Okay, so this is equal to the del of the rho u with respect to delta x. Okay, and then the rest of part is the delta f, delta y, delta z, and delta x. So let me just write this explicitly. Delta x, delta y, delta z. So this good news here is this is the after you evaluate this is nothing but del rho u times del rho u del x times the volume v. Okay, so this is the this one quantity that we wanted for the m of the net x. Any questions for this argument or calculation? If you are okay with this, then now let's take we just make a shortcut here. So now similarly, now we want to consider this the m dot net in the y direction. So if you see the similar structure here, right, it should look like del of the rho times v del y times v, that is for the m dot net y. And then lastly in m dot net in the z direction should look like d rho w d z times the volume v. So this is not bad. This is not bad. So it's going to give you overall m dot net is going to be we have a common term of the volume. Then you can just put this d del rho u del x plus del rho v del y plus del rho w del z. Okay, so this is the for the m.net. Any questions on this? Okay, so then this is great. So the now combining all together. By the way, what I think it is alright. We can still do this, but combine all together. What we are getting here is d is 0 equals to I just write it again. dm dt of d is cb plus m.net, and then this one equals to 0 equals to the first term was d dt volume. Second term is going to be d rho u dx plus d rho v dy plus d rho w dz times volume. Okay. And in this case, volume is the it's an infinitesimal, but this is still the some constant value, right? I mean some value. So you can just divide everything by the volume. So overall, what we have here is d is 0 equals to 0 dt plus dt plus rho d rho u dx plus d rho v dx plus d rho w the middle one is the dy. Okay. This one is the final form. Yeah. Okay. And then so this one is okay. Basically, what this slide explains how we calculated it, and then the combining all together. This is the equation what we got in the top here, and then this equation has a name. This equation is the same as the mass conservation, right? I mean the same as what we did for the mass conservation in the control volume analysis. So this is also called continuity equation. The only difference here is we are concerned with this infinitesimal volume rather than the big volume, right? So that is the only difference. Okay. Any questions? Any comment? This is sort of beautiful with lots of symmetries and such, right? And in fact, with using some notation, we can simplify the notation a little bit here. So let me put some comments. Okay, simplify notation. We have been using this, our favorite friend, this number. This is the I ddx plus j dy plus k of dz, right? So just to give a little thought about how we can simplify this notation with this number. You can see three terms. Each of them has the ddx, ddy, ddz, right? And then this is multiplied with the same thing. So you want to know how to, you think about how to simplify this. One thing always you want to think about here is this quantity shown in this continuity equation, is this vector or scalar? It's a scalar, looks like, right? So it's a scalar. So if you want to use this, lambda itself is a vector. So there you have to consider how to convert vector to the scalar. And the most simple or most common way is the dot product, right? When you make a dot product of a vector, this becomes scalar. So the let's see, okay, this is the scalar equation. Okay, so in fact, you just need to see after you see it. This is okay. It's a bit obvious, but dt. Okay. So the second term, right? Okay. If you remember this velocity is also vector, right? Okay. U times I plus V times J plus W times K. Right? This is the velocity. And then if you look at this particular quantity, rho times V, okay, then this is going to be rho U times I, rho U I plus rho V J plus rho W K. Okay. So now if you have the careful, if you make a careful observation by taking the dot product of this nabla with the rho V dot product, then you can reproduce whatever is in this square bracket. Okay. So this is nothing but nabla dot product rho times V. Any questions for this? Yeah, this is let's again we see a lot of this in this class. I mean at this point, especially in this Navier Stokes equations topic, we see a lot of this kind of these three-dimensional vectors. Right? So let's the refresh memory once again and then get used to it. Right, that's good. If this is okay, then the assumptions we can make. So this is a really good point, right? So far, we have never made the assumption that fluid is the incompressible or compressible, right? So we can make such assumption, but let's go step by step. So one of our favorite assumption is the steady, right? Steady assumption. If you make a steady assumption, what can you say about this continuity equation? So let's say this is the star, equation star. If you have a steady flow, the assumption is always ddt term is 0, right? So this equation star is going to be 0 equals to 0 equals to nabla dot rho. Okay. So this is one of the constants here. Okay. This is
for you to
steady flow.
accept there is going to be hard.
Okay, not bad, right? And then another thing is
I see someone crying.
if we make a incompressible flow, okay, incompressible fluid. Okay, if we make this assumption, okay, the first one is let me just say ddt term is equal to 0. Okay, incompressible fluid by right, the assumption here is giving you rho is the constant as constant. Okay, rho is constant. Okay, so let's forget about the steady flow. Let's make this incompressible assumption independently of the steady flow assumption. Okay, so then what happens to this the equation star here? What can you say? What can left hand side still remains 0? What can you say about the d rho dt if you have an incompressible fluid? 0, right? If you take a derivative of constants, then it should be 0. So this is going to be 0. What happens to the second quantity? In this case, rho is constant, right? So rho is constant value can be taken out of the derivative. And then just divide by the that quantity. This equation is going to be 0, right? So in fact, what remains here is going to be nabla dot b only. so this one is the important part here is the regardless of steady steady assumption. So this second equation can be is only as a result of incompressible assumption. Regardless of if the flow is steady or not, this is just always in this case. So by having the incompressible fluid, this continuity equation is really simple now.
Sorry.
Yes.
How come your rho disappear? I thought you can just bring it out of the derivative.
But
you
if
still
you
have
bring it out, what about if you divide the entire equation?
Sorry, come again?
If you take out the law out of the parentheses, right?
Yeah.
And then can you just divide it? It's a constant value.
Also, you divide it over.
Yeah, you
okay.
can divide it by, yeah, that's good, yeah. Thank you very much for the question. This is nice, right? This kind of small steps, yeah, unless you follow, yeah, it's very easy to, do structure with. So yeah, thank you for asking. This is great. So these are two assumptions we made here. Okay. So here, in fact, okay, so this is the two particular case of the steady flow or incompressible flow. You can reduce this continuity equation to the relatively simpler expression. Yeah. Great. So thank you very much. Absolutely. Any questions for this? Okay. Let's go to the next. I just make a last. This is sort of a fun topic, but I can just give you the alternative derivation of the continuity equation. I mean, you should know, right? There's nothing like you don't have to know. It's okay, it's always fun. I mean, by talking this, I just want to introduce, there's some different mass identity and such. It only takes 5 minutes. Okay, so it's not bad. Okay, so alternative derivation of continuity
What that is.
Okay, so let
You're protecting me,
let
that's
me
why
come
it's
back and start from where we started here. Okay, we have 0 equals 2 dmdt of the control volume plus
You know the Stokes equation that's
surface integral control surface of the low
unsolved.
v dot
Like you can never find a solution.
Okay,
It's still a
this is
mathematical price.
this is
you can find
directly
anything
from
you want. Like, sure.
directly
It's
from
quite
the
interesting. Like there's
Reynolds
no
transpose theorem.
solution for
Yeah.
something. I don't
So
know. Like no
now
one
okay,
can find
we
it.
can also do this is A and B. Okay.
No.
I thought they say all those complex
Okay. So
formula, hopefully you converge to one simple.
for this one, right?
Back to reality.
I actually like this because this is a bit more beautiful.
Here's
So
something else. Here's
the
one.
Any substitution.
this A, right? Yeah. Okay, so A is this dmdt term, right? Okay, dmdt term of the control volume. For this one, I think this is all right because okay, let's see let's see the ddt of the if you integrate law for the entire control volume, this is what you're supposed to get. Okay, so the this one is no, this one is no confusion. And then we make a similar assumption here. Now, okay, this dB is this. We are looking at a particular location of x, y, z, right? And then this ddt is a total derivative, but we can actually look at the particular location. So let's just bring it in to the integral. But the consequence is this become a partial in terms of expression in the key of the dB. Okay, so this one is the one of the by looking at the specific location of the expression. Okay, that is the part A. How part A can be simplified. This one is just a bit more mathematical here. In fact, for the second one, the surface integral of the low v B dot dA. Hey, this one is the in fact the can be simplified super well. The if you remember this one thing from your vector calculus, divergence theorem. Have you ever even heard of this? Okay. This is again, it's more like for your information, but it's good to know this theorem.
Oh, yes.
So this divergence theorem, right, is if you take a surface integral of some vector, okay, if you take a surface integral of the some vector for the entire surface, if you take
It's
this
like, I feel like moving
some
like
vector
this.
for the entire surface,
I think
this is
moving
okay.
got
In this case,
This
this
is
I have
dA
thank you.
So
is
Yeah, the
the
curve,
NDA.
yeah.
good luck to him.
Then what you are getting here, this is going to be converted to the volume integral, which is the volume integral of the divergence of this vector. This particular theorem is simple math. It's actually not simple, but this is coming from the mathematics. Okay? This is not, the derivation is you need some consideration, but the result is simple, right? This is whatever you are integrating from the for the surface integral, then that's going to be the converted to the volume integral. That's closed surface is going to define. Then this theorem is has a particular name. It's called divergence theorem. So the deriving this is not our interest, but this is a mathematical identity that people can use, right? And then can you just try to think how by using this theorem, how can you simplify this? Okay, I'll give you 1 minute. Just see the see the pattern recognition, right? If this given this theorem, how can you simplify this surface integral? In other words, this f is a generic vector, right? General vector. I just use this vector, three-dimensional vector. What is corresponding to the f in this particular case?
B?
Low times b, right? Yeah, it's going to be low times b. Is corresponding because I just looking at the rest of the part is the low b, right? So it's going to be, if you look at this, it's nothing but the nabla dot low b db. Okay. So this is good. Now what we have here, so they combine this overall. This is going to be what we have here is the if you combine a and b together, what you should have here is 0 equals to this a is the integral of the control volume d rho dt of the dv plus for the same same integral of the nabla dot rho b dv. But the good thing about this is for these two integral, now integrand is the same, right? Now you can combine them. So the integral of the cb equals to d rho dt plus nabla dot rho times b of the dv. Okay. This is the condition we have to have, right? And then since this one must be equals to 0, integral of something must be equal to 0. This is for this to be always
Okay, using
true.
his mind.
Whatever inside must be 0, right?
Shake it.
So now we can uniquely say this one must be 0. So 0 dt plus nabla dot rho b equals to 0. So this is another derivation of the continuity equation. Okay. So how was it? This is not bad, right? 5 minutes, but
But
we,
it's
we
beautiful.
didn't. I mean, in this case, we didn't even think about any flow or anything. Indeed, we just use this particular theorem called the divergence theorem. Yeah, so the, I mean, again, this is more like, if I just show this, right, then, perhaps, okay, what the hell, right? But anyway, yeah.
So just to check, the first time you derive it is based on a small control volume, but then this one you are skipping the control volume, you just use the divergence theorem to form the same
Yeah,
thing.
it's okay. So we are not using this. This is particularly small. You're right. Yeah. In this case, for the second derivation, we are not. For this being small. For this being small, actually, it is still relevant at this point.
Yeah.
At this point, when you bring this DDT inside of this, right? We sort of made assumption. We are looking at the infinity small location.
Yeah.
So in that sense, this is still carry on this small
Yeah.
thing. But overall, right? This derivation for the second part, it doesn't have to be small.
So the main difference is in the way you derive the part B. Oh, okay.
Yeah, the main part is, yeah, you're right. So the main part is whether we consider what's coming in and out.
Okay.
Right,
Makes sense.
yeah.
Thank you.
Yep. But this is, I guess, this is another thing, right? Mathematics is beautiful, right?
Because this one, right,
I sort of
from the
love
part
that.
B,
I sort of
right,
love this.
you must look at
Right.
control volume.
Any
Then you
any
must look at
other
the axis.
any
But then
point here?
if you do this method, right, you don't even need to care.
Okay,
You can
then,
skip. You just you got the
the,
theorem, then the
let's
theorem will
go for
straight
the,
away skip.
let's really go into this, last,
Mainly
Newton's
for the-
second
like
law.
conceptually,
This is the
this
second
one
step.
you don't
Okay,
need to
that
care.
is
You don't need to
Navier
know
Stokes
that you
equation.
don't need, yeah, don't need to do in out. You don't need to do all this, but it will give you the same thing. Like in splitting up.
Newton's second law eventually going to be a Navier Stokes
Always
equation.
change the style. Like, cannot, sometimes you can blindly follow the theorem, sometimes you must.
For this one, right, okay, I just want to recap here. I just, see, this is still only a week 10, but I sort of want to summarize some journey we have been taking, right, okay. So this is, okay, we go week 2.
So this is something on.
Okay, week 2 is just, second week we met, and then, I've been speaking something, right? That time we have been talking about the hydrostatic equation. And then for this one, right, we are looking at some, we made this kind of assumption always, right? We consider this hypothetical volume of the fluid, and then this fluid have, they got some weight going down. Yeah. We also have this guy have some force due to pressure, right? And then we have been using this delta F. We consider delta F for this guy, which is the okay, let's say the pressure force acting on this guy plus weight acting on this guy, and then this one must be equals to what was the argument when we did it for the hydrostatic equation? It's all the fluid element was
Zero.
I mean, this is not moving, right? So it's supposed to be equal to 0. Okay, so this was the where we started. Okay, this is where we started. Okay, and then this one is going to it actually gives you the what was the equation again?
Magic formula.
P plus gamma z. This is going to give you P plus gamma z is the constant, right? This is the hydrostatic equation that we get. Right, so at different locations. Okay, so this is something you may vaguely remember here. Then now we can go for the weeks. We also did the weeks 3 and 4. Then we discussed the Euler's equation. And then this Euler's equation becomes Bernoulli equation. And then what we did in this case here is it's a good contrast with the week 3. Okay, we did the same thing. Okay, now we are considering this guy is moving, right? This guy is moving, but this guy still experience weight, and then there are some pressure is acting here. So now let's do this. Okay, force is the f of the p plus weight, okay? And then, in fact, you know, the argument we made in the week 3 and week 4, right? This one is not 0 because it's moving. And then, what can we say? This is equals to ma, right? Okay. So this equals to ma, and then if you remember, we had a different expression for a, right? Acceleration, you know, the along the streamline, acceleration across the streamline, or acceleration in the Cartesian coordinate. Yeah. So this is this is giving you the in the case of the Cartesian coordinate, what we are getting here is p plus gamma z plus half rho b square equals to constant. Okay. So but still, one of the major assumptions we are making here. What was the one? I mean, we made a lot of assumptions, but you know, look, I can write it down. Everything was steady, incompressible, and inviscid. Okay, and then one of the major assumptions we made here is this being the inviscid. Inviscid is we never consider we never consider the viscosity or shear stress. Okay. So now, okay, we come back to the week 2, week 3, 4. We come back to week 10. Okay, this is a new. Right, something new here. It's the Navier Stokes equation. By considering how we sort of evolve, right? Okay, we are doing the same thing. Okay. We only have one pattern of thinking, right? Okay, we consider this fluid element. This fluid cube experiences, for example, okay, weight. They may get some f of the p, which is the pressure. But today, right, now we consider f of the s, which is shear. Okay, so now the consideration is going to be different, right? What we are getting, what we are getting here, this sum of the force this consists of the 3 different components. One is the pressure, let's say f of the p. Another one is weight, which is going down, or you know, going along the gravity. And then now we have to consider the shear, which is the f of the s. So this is a new component. Okay, this is a new component, and then this f of the s is making the equation a lot more difficult to solve. Okay, but the idea here is again we are considering considering a static system or dynamic system. We are considering flow, right? So this should be still equals to ma. So now we are having some more complex equation. In fact, you know, now we cannot integrate. It's a bit more difficult. We have to play with the differential form. That is Navier Stokes equation. But this is the difference here is we are considering the viscous flow, and then shear stress. So shear stress is something negligible. Okay.
You could take a
So
look.
this is sort of a 3 steps, right? How things evolve in this fluid mechanics class since the beginning. Okay. This is I mean just as a quick recap. But any questions conceptually?
Triangle.
Okay. Is it okay? Okay. So then you know that let's start thinking about how we can analyze those
You can
things.
understand.
Okay.
You do before.
Right. So
Do before, but
the
understand it's 2 different things.
Yeah. It's a bit like King Boy.
Oh, serious? Fucking time. Oh.
So we do the same thing, okay? We do the same thing now. We want to consider this little nice box of the fluid. And then this fluid,
He starts at DG.
the
He starts
middle
at
part
DG.
is the
He
X.
starts at DG.
Oh, something.
Yeah. And he don't learn some of the stuff because he's a chem engineer. So he
This
doesn't
one
need
is
to
delta
learn
X.
some of the
Yeah, this one
This one is delta Y.
this one probably can. But I think it's
This one is
probably
B is equal to
it's like you don't use it.
And then now we
You won't find
want to
it.
consider
Yeah.
what
I
kind
work
of
in a
force is acting
pharmaceutical
on
company,
this guy.
GSK,
Okay,
good
so
vaccines.
okay, let me just give you a few
So I guess system
parameters.
control
Okay,
will
the
learn also.
low is the density
What
of
else?
this,
The one
the
is
fluid
just
inside
the
of this
form,
tube.
right?
This
Next to chemical.
volume
But
of this
anyways,
tube
the symbols very different.
is the
anyways, symbols
del
very
x,
different. So you probably
del
don't do
y,
like the same
del x,
exact
del
thing.
y,
But yeah,
del
probably
z.
do lah,
This
right?
is something as we defined here. And then we can also say mass of this volume, mass of the fluid particles, which is in this particular control volume here with d rho times b. Okay, and then this is nothing but rho times del x, del y, del z, depending on the context. Yeah. Great, I think it is okay. This is more like a setup. Here now, we consider three forces. This is just a repetition of what I just said. One is the gravity. Another one is the force due to pressure. And then last one is the viscosity, shear. Okay. By the way, we can, this is more like just a naming here. In this case, okay, they have on the slide as well. They said, the force can be broadly grouped into the two categories. One type of force is called body force, which is a force that is acting on the entire mass. Okay? And then another one is called surface force. Surface force is the one that is acting on the surface. Okay? As the name suggests. Okay? So in this case, pressure and shear. If you know, or maybe I shouldn't say the answer, but answer is actually on the slide. But of those three forces, right? Which forces do you think is the body force? Gravity, right? Yeah, gravity is not only the surface, right? It's acting on the entire location. So this one is the body force. And then what about the pressure and shear? Shear is the friction, right? Or the friction happens, it's only touching the surface, right? So the friction is the shear is the surface. Force pressure is also acting on the surface of this particular thing. So these two are surface force.
Oh, in the homework.
If let's say
Okay.
then everything changes.
Also, this is not too much about our interest. What about the magnetic force? If you have a magnetic object, right, and then the forces, you put it into the magnetic field. It's a body force, right? It's not only the surface. What about the electrical force? The same thing, right? If you have an entire object has the conductor, for example, and then if you place it into the electrical field, that's going to express the entire body is experiencing. So there are many different types of body force has besides gravity, there are different examples. Okay? But in our particular case, okay, we are looking at the gravity as the body force, and then the rest of the two things as the pressure and the shear is the surface force. Okay, so let's start analyzing what each of the quantity looks like. So first quantity is the weight. Okay. So this weight is not bad. In fact, you have this particular object and then going downward. This is the weight. Actually, for the consistency of the notation, let me write the force of the W. Let me just write it. Okay, F of the W. Okay, and then in this case, this is we don't need much of the discussion. I think we have F of the W is equal to mass times gravitational acceleration, right? mg. And then in this case, m is nothing but rho times b times g. Okay. Any questions for this? This is super easy. This is actually super easy here. By the way, if I make something a bit more difficult here, in fact, right? This is the vector. Okay.
The only easy form of last time.
Yeah. This one is the vector, right? So we need to, in fact, we have to consider this as a vector. So
This makes someone with
consider direction.
A joke. Questionable.
I prefer that one to this one. More
Consider the direction.
more
In fact, this FW
nice, nice.
equals to
Yeah, I have.
m times. In this case, right? Let's associate the vector with this gravitational acceleration. Okay.
Linear algebra.
That's
Okay,
some,
so in
oh
this
yeah.
case, I mean,
That's some too.
if you consider direction, this f of the w equal to mg equals to rho times v times d vector.
No, it's now see which term subject pop up the linear algebra.
And then I just explain what this means. This g of d is vector, right?
I think the ODE,
This is usually
the ODE
is
makes
the
sense.
minus g
Linear algebra.
k in common in
Remember the part where you say the ODE with particular solution?
Or
That's
in
near.
conventional notation.
Basis vector.
Okay.
oh yeah, linear complex.
This one is not as easy. I mean, this is just a more maybe new concept, but does it come to you naturally? Okay, I just want to here, right? In general, what we are looking here, weight is always going downward, right? And then usually in the way we are used to, we define this, z direction is going up and down, right? So usually but in this particular notation, we associate the direction to this gravitational acceleration. Okay, and then this g vector usually is pointing to the minus k direction with the magnitude of g. Okay. So this is just a bit of the different notation here. But any questions for this? Right. Then if you're okay with this, let's go to the second one, which is pressure. Pressure force is the F of the P. Okay, so in this case, okay, I'm going to do the similar argument. But now, before doing anything, okay, this F of the P is also vector, right? This guy is a cube. This particular fluid element is a cube. And then they have three directions, potentially. So let me just consider this Fp in the x direction with the I, plus Fp in the y direction in the j, Fp in the z direction for the k. Okay, let me just write it in this way, considering the three directions. Okay, so to do this, okay, let me just just consider f of the p first. Okay, to do this, I do exactly the same as in fact, you can use quite similar arguments. Okay, we are looking at this box from the side view, and then at this point, okay, let's say this is the x direction. Center of the box is x. This box has the length of the delta x, right? So the front is the x plus delta x over 2. Back side is the x minus delta x over 2. It's okay, right? Now we want to consider two forces. The force pressure is always coming from the the pointing to this box. So there are two types of forces. This force. So pressure in the front is the P, which is evaluated at this location, Px plus del x over 2, which means the pressure evaluated at this coordinate. From the back side, you have a pressure x minus del x over 2. This is alright, right? And then now we have okay. Well, this is almost the same, right? As those mass flow, right? If you are listening to me 20 minutes ago, I'm sort of copying the same thing. Yeah. So we have two surface. We have a surface here. In this case, how big is the surface area? The y delta z. Yes, thank you. The y delta z. So this is not bad. So let me try to explicitly write what is the pressure. Okay. In this case, if P in the x direction is going to be, let's first write the front part. Front side is the force is pressure times area, right? So it's going to be the Px is minus because it's pointing backward. Px plus delta x over 2, which is the times delta A. Okay? And then this is the front. And then for the backwards, it's pointing in the positive direction. This is going to be the Px minus delta x over 2 times delta A. This is the back. Okay, this is not bad.
So, Prof, where's the front again?
Front is the A. Okay, so this is the front side.
Oh, okay. Okay.
I mean, yeah, this is quite arbitrary. Yeah, this is what I mean by the front and back. Okay, so in this case, okay, let me just try to group up things. Okay, let's take a minus and then P of the x plus delta x over 2 minus P of the x minus delta x over 2 times, okay, delta A is the common factor, which is the delta y, delta z. Okay? So I just, so we know, perfect out. And then we make the same argument. We just do the, this sacrificial delta x, okay, multiplied by delta x, divided by delta x. Okay? And then for small delta x, the first part is nothing but differential form, right? So it's going to be dp dx. So this is the minus dp dx. Minus dp dx times delta x, delta y, delta z is the volume, right? So this is going to be the volume. Wow, this is beautiful, okay? Isn't it? Yeah, it is, I think it is beautiful. Yeah, but that's good. So we can do the similar argument. Similarly, we can have f of the py is going to be, I can write in the same way, dp dy of the volume. F of the pz should be minus dp dz the volume. Okay, so now overall what we have here is the f of the p has a 3 components. Okay, the common factor is the the minus volume, right? So let me just factor it out. What you should have here is the dp dx in the direction of I plus dp dy in the direction of j plus dp dz in the direction of k. So this is the expression for the pressure force. Well, that's not bad. If I just be a bit more, try to be a bit clean, how can I just write this in a cleaner way by using Navier? Minus volume times the so Navier is I just write this. Navier is the I ddx plus j ddy plus k ddz. So in fact, this is nothing but Navier. In this case, it's not the dot product, right? This f of the p. One of the things here you may want to pay attention. This f of the p is a vector, right? So Navier shouldn't be applied to the vector because otherwise it's gonna be a dot product. I mean, it's gonna be a scalar, right? So if you directly apply this to the p, then you can get this expression. Okay, so this is good. Now, super nice. The good news is we have found this is the one of the force weight. We know the weight expression for the weight, and then we know the expression for the pressure. Then the last thing is that we need to know the expression for the shear. Okay, so that's the number 2, right? So number 3 is the shear. And then so you can say shear force. Let's say this is the F of the S. Okay, so this is going to be, let me just write in a similar way. F of the S of the vector should be F of the S in the x direction in the I, F of the S in the direction of the Ej, plus F of the S in the direction of Z. Okay, right? Okay, so in this case, okay, I'm going to just explain this, but this one is a little bit more complex than the previous cases, because you know when you want to consider shear stress, right? At this point, for example, you know, let's say you know in this case, okay, for the sake of discussion, let's say this is the x direction. Let's say this is the y direction. This is the z direction. It doesn't matter, you know, however you define it. But for the on the surface, right? On the surface that's facing in the y direction, on this surface, you are supposed to have potentially 3 forces, shear forces, right? You can say the same thing. On this surface that is facing the x direction, you are potentially have the 3 direction forces. Same thing for the front, which you also have the 3 forces. Right? And then now, if you want to know, the what is the S of x, right? You need to actually consider this guy. You need to consider this guy. You need to consider this guy. In addition to this, you know, the 2 other surfaces that is hiding here, right? I mean, actually, 3 other surfaces that's not explicitly shown here. So this is to consider this, right? The problem here, or difficulty here, is the shear and the normal stress. Okay, at all 6 surfaces on the fluid, on the fluid element in x direction. Needs to be considered. Okay, so same thing for the f of the sy and f of the sd. Okay, so in fact, you know, this is quite tedious, and then if you want to know the proof, okay, the derivation is I love derivation because this is, you know, it's a really good way to, you know, get familiar with the topic, right? But this one derivation actually, you know, is super long, so I don't even try to do it in class. Okay, but instead, okay, and then this is also the some, you know, the consideration is really complex, and then it's maybe beyond, you know, the something necessary for this class. So I'm going to, you know, share you with some reference, which is, you know, you can go through the derivation, but this is actually the real FYI. You don't really need to remember this, okay? But what is important is let's get the result. Okay, the result here is going to be
the acceleration, back fidelity also F, right? Ask you
so
to prove
result
the
is
back
actually
fidelity.
very good for Newtonian fluid.
Ask you to
For Newtonian fluids, okay, the f of the s can be really simply described by the volume of the fluid element times viscosity times number square, which is applied to the vector. Okay, this is the sum of the after you derive it. With the assumption that the fluid is Newtonian, we can reduce this force to this form. Okay, so let's say, you know, the derivation. Okay, textbook reference will be uploaded on the e-dimension. Okay. Actually, this is a one lecture note, which is coming from MIT that we used to use. But this one is the again, just purely for your own information. What is more information is the let's remember this form. Okay. After considering all the forces, all the direction, this force can be reduced to this form. Okay. So that is one of the outcome that you may want to know. Okay, so with this, right? What I just just not to forget. My starting point is we wanted to consider three forces acting on this fluid element. Okay, so the now total force. Total force F, sum of the F is nothing but F of the weight plus F of the pressure plus F of the shear. You have a three component. And then if I write it explicitly, F of the weight is going to be the rho V G. G is a vector. For the pressure, is D nothing but this is the term is a minus. So minus minus number P minus number P times volume, and then for the shear is the volume times mu number square P. This is the force. Okay, so this is not bad. Then consider the F equal MA. If you consider F equal MA, this is going to be let's say the F is going to be let me just factor out the volume. In this case, this is going to be here. So volume times rho G minus double P plus mu double square V. Sorry, this is the force. Okay, this is the sum of the force equals to MA. Okay, and then just to record here, acceleration vector in the Cartesian coordinate. When you have a flow, right? This is nothing but dv dt plus b dot number b. This one is acceleration. Okay, so this one is going to be m times dv dt plus b dot number. Okay, so this is nice. Okay, this is the equation, and then divide everything by the law, right? Okay.
Oh my God.
So so if you divide by this is going to be the law. Okay, divide by volume. What we are getting here is the rho G minus number P plus rho G minus number P plus mu number square V
番字碼嗰 BM， 你嗰度咪個字
dv dt plus
we ask them for true answer, tell them.
V.
Come FM, they no, yeah.
This is the
This one is
final form.
further,
Okay,
tell
this
you.
is super cool. This one is
Better
called Navier
press the
Stokes
guy.
equation.
He divide by what? Divide by
Okay,
B.
so this is great. Yeah, it's just 4 o'clock. So we just derived Navier Stokes equation. although I skipped this shear force part, but yeah, we still got this. Okay, so just as a quick preview for the tomorrow. Okay, this is the if you want to write the Navier-Stokes equation by the component form, this looks like this is quite messy here. Okay, I explained how we are getting this before, but this is the okay. Just as a comment here, right? This is comment. My last comment here is this is the vector equation, right? Navier-Stokes equation is the vector equation with three components, x, y, z component, right? So in fact, this equation can produce three different equations in the x direction, y direction, and the z direction. Okay, and then those are the three directions on the top here. This one is just a bit extra. If you change the coordinate system, you have a different form of Navier-Stokes equation. But this is for now. Just don't forget about. Don't worry about this. This one is the if you expand this equation, you get those coordinate. But anyway, that is all for today. Let's come back to this point tomorrow, and then let's use this equation to solve our systems here. Okay. Right, thank you very much for your attention, and then I'll see you tomorrow. Okay.
不要了，不要了，不要了，不要了，不要了。